Welcome to my fourth tutorial in statistical thinking titled Visualizing and Summarizing Sample Statistics. At the end of our second tutorial, we briefly discussed the concept known as sampling variation, how sample statistics vary from sample to sample. Sample statistics vary from sample to sample and are all estimates of the unknown population parameter of interest. Therefore, we have to reason not only with the sample statistic we obtained, but also with the sample statistics we could have obtained from other samples in order to make a statistical decision regarding the true value of the population parameter. This sort of reasoning can feel quite confusing and challenging at first. The concepts we will study over the next three tutorials, corresponding to chapters 6, 7, and 8 in my book, are the foundations of statistical inference or analysis. Laying down foundations are never easy in any context, so it's important we reason with the concepts slowly and thoughtfully, one step at a time. We will start with a hypothetical example. Let's say you want to estimate the population mean height of male students at your college. You decide to select a random sample of 16 men and measure their heights. The sample mean you calculate from your data turns out to be 70.3 inches. You are interested in understanding variation in sample statistics, so you decide to collect another sample of 16 men's heights. This time the sample mean height is equal to 69.2 inches. You are not surprised that the sample means are different in each sample because they are based on different samples of individuals. However, you would like to get a sense of how much they will vary if you were to repeat this process of sampling numerous times. You decide to repeat this process 10 more times, resulting in 12 sample mean heights based on sample sizes of 16 men. The resulting 12 sample means are shown here. At this stage, the following question might come to mind. Why does the range of sample mean heights go from 68.3 inches to 71.4 inches? In reality, the 12 sample mean heights you observe may not vary as much as we see in this hypothetical example. If you were to repeat this process a very large number of times, this is a probable range within which you would expect most of your sample means to fall. However, the variation in sample means you expect in each sample is based on making particular assumptions about the characteristics of the population of interest. According to the top Google search result, the currently accepted population mean height for young men in the US is equal to 70 inches. The value for the standard deviation is not given, but 3 inches is considered a good estimate. Therefore, according to the empirical rule for the normal distribution, we can state that approximately 95% of individual heights lie within two standard deviations of the population mean height of 70 inches, or between 64 inches and 76 inches. For now, we will assume that these population parameter values are the true values for the population mean height and standard deviation for young men in the US. Let's stop for a moment and think about what we have reasoned through so far. You might be thinking to yourself, I thought the whole point of statistical analysis is that we don't know the population parameter, and we are using our sample statistic as an estimate of that value. Yes, that is true. However, before we can do that, we first need to understand how sample statistics vary around the population parameter from sample to sample. The only way we can do that is by first assuming the population parameter is equal to a particular value, and then visualizing how sample statistics, based on a particular sample size, will vary around that value. We first need to ground these abstract concepts in reality by assuming a particular value for the population parameter, in this case the population mean. By assuming the population mean is equal to a particular value, we can determine the distribution of sample means around that value, a distribution known as the sampling distribution. First, in theory, we establish what the sampling distribution looks like for a particular value of the population parameter. Then, in reality, we can use the concept of the sampling distribution, along with our sample statistic, to make statistical decisions about the unknown value of the population parameter. Let's continue with our example of selecting samples of 16 men and calculating the sample mean heights. Assuming that the population mean height of men is 70 inches, if we were to repeat this process a very large number of times, the distribution of sample mean heights would look like what we see in figure here. The blue histogram is a histogram of sample means based on 10,000 simulations of random samples of 16 men's heights. The number 10,000 is not important here. It is simply enough simulations to clearly see the underlying distribution of sample means known as the sampling distribution. As we can see, the sampling distribution follows the normal distribution with approximately 95% of sample means between 68.5 inches and 71.5 inches. The assumed value of 70 inches for the population mean is right in the middle of this distribution. It is the mean of all the sample means. In other words, the average of all sample statistics is the truth. The next question to ask is why 95% of sample mean heights are approximately between 68.5 inches and 71.5 inches. How do we measure the variation in sample means around the population mean? A statistic very similar to the standard deviation, called the standard error, is used to measure the variation in sample means around the population mean. Whereas the standard deviation measures how far we expect an individual value to deviate from the sample mean, the standard error measures how far we expect a sample mean, based on a particular sample size, to deviate from the population mean. You will notice that in the calculation of the standard error, the sample standard deviation is on the top of the formula and the sample size is on the bottom. What this means is that the larger the sample size used, the closer we expect our sample mean to be to the population mean. This should make intuitive sense. The more data your sample statistic is based upon, the better an estimate will be of the truth in the population. In other words, the more data we collect, the closer we expect our sample mean to be to the population mean. In our hypothetical height example, using a sample size of 16 and an estimate for the standard deviation of 3 inches, the standard error is 3 over the square root of 16, which is equal to 0.75 inches. Therefore, according to the empirical rule of the normal distribution, 95% of sample means are approximately between 68.5 inches and 71.5 inches, or within 2 standard errors of the assumed value for the population mean of 70 inches. This results that the distribution of possible sample statistics based on a particular sample size follow the normal distribution is known as the central limit theorem. We will reason around this result to make statistical decisions about unknown population parameters of interest. However, whether or not this result is valid does depend on certain additional assumptions covered in my book about the quality of the sample data. Again, the quality of our analysis always depends on the quality of the data it is based upon. In our hypothetical height example, if we were to select a sample of 36 men, the standard error would be approximately equal to 0.5 inches. We'd expect 95% of possible sample mean heights to be within 2 standard errors of a population mean, or between 69 inches and 71 inches, assuming that the population mean is equal to 70 inches. In other words, there is a 95% chance or probability that our sample mean height will be between these 2 values. There is only a 5% chance of obtaining a sample statistic more extreme than these values, or more than 2 standard errors from the population mean. If we were to select a sample of 144 men, the standard error would be approximately equal to 0.25 inches. There is a 95% chance or probability that our sample mean height would be between 69.5 inches and 70.5 inches, a very narrow range of values. There's only a 5% chance of obtaining a sample statistic more extreme than these values, or more than 2 standard errors from the population mean. As we can see, as we increase our sample size, the closer we expect our sample statistic to be to the truth in the population. We have seen that the larger the sample size, the narrower the sampling distribution of possible sampling statistics will be around the population parameter of interest. This is a very powerful result that we will make full use of in the following tutorials. In reality, we don't know what the population mean is. However, what we do know is that our sample mean, if based on quality data, is one of a range of possible sample means that are normally distributed around the population mean, whatever that population mean may be. Let's complete this tutorial by looking at a more concrete real-world example. From a statistical point of view, elections are interesting because it is one of the rare situations where we know the population parameter, proportion voters who voted for a particular candidate once the results are counted. In a run-up to a national election, particularly in the US, there will be numerous organizations conducting election polling. From what we have learned in this tutorial, we can say that we expect the average of the results of all polls conducted to be equal to, at least in theory, the result of the election. For this to be true, we have to assume that each pollster selected a random sample of voters. Valid weighting, a concept discussed in my chapter on polling and surveys, was implemented, and the same sample size was used for each poll. In reality, the polls will not be based on the same sample size. Different sample sizes are not a big issue when calculating the average of poll results. As long as each poll was otherwise well conducted, the average of poll results can be calculated by weighting each individual poll result according to sample size used. The website Read Clear Politics calculates the average of polls leading up to elections and tries to predict the election result. In the 2008 general election on November 4th between Barack Obama and John McCain, the election result was 52.9% for Obama and 45.6% for McCain. The average of the polls leading up to the election from October 29th to November 3rd was 51.1% for Obama and 44.5% for McCain, not very far from the actual results. To summarize, in this tutorial, we have defined a framework for describing how sample statistics are distributed around an unknown population parameter. As long as our data adheres to necessary assumptions and conditions, our sample statistic will be one of a range of possible sample statistics that distribute themselves according to the normal distribution, centered at the unknown population parameter of interest. The distribution of possible sample statistics is called the sampling distribution. The larger the sample size, the narrower the distribution of possible sample statistics will be. We measure the variation in possible sample statistics around the population parameter using standard error. It measures how far we expect our sample statistic to be from the population parameter of interest. Since the sampling distribution is normally distributed, approximately 95% of possible sample statistics will be within two standard errors of the unknown population parameter. In the next tutorial, we will use what we know, our sample statistic and the result of the central limit theorem, to reason to a statistical decision about what we don't know, the true value of the population parameter of interest.